Let's review our AC source conversion. Here in the first problem, we have a voltage source with series impedance. So the first step would be to calculate our series impedance. So we've got two resistors, a 5.6 and a 2.2. So we would add those for the resistive portion of our impedance, plus 8.2J, which is the reactive portion. So that gives us our total impedance of 7.8 plus 8.2J, or 11.32 at 46.43. Okay, so once we do that, it's just an Ohm's law calculation to get our current source. So if we're looking for the source current, it's going to be E over that series impedance, or if we're looking for E, it's going to be I source current times the parallel impedance, where the series impedance equals the parallel impedance. Okay, so here we're looking for the source current now. So we're going to take our 20 volt source and divide by this impedance that we just found. So that gives us a source current of 1.77 amps at negative 26.43 degrees. So the next step would of course be to place our current source in parallel with that now parallel impedance that we got simply by finding the series impedance from the voltage source. So that would be the source conversion, and these two are equivalently the same source. Or they would actually, when we do a source conversion, what we're saying is that when we apply a load out here, some kind of load, that the voltage and the current would be the same no matter which source we use. Okay, so remember, that's really what we're saying, is that IL in both cases would be equal and VL would be equal as well. So, and you can even plug in some impedance on your own there and check to see that that's indeed true. All right, so let's look at a current source that we're going to find the equivalent voltage source. So here, again, we're going to take our parallel impedance, and this time we're going to take both the resistor and the inductor, and we're going to find our ZT. So we did the product over the sum, so the resistor impedance times the inductor impedance over the sum of both. And then that gives us the impedance, and I'm going to maybe stick to the rectangular version here for a moment, because that's really what we're going to use when we draw our resulting voltage source. Okay, so to find that voltage source, we're going to multiply the current source by that parallel impedance, and that's going to give us our voltage source. Okay, so we are going to redraw our circuit with that voltage source, and then with our ZT, it now becomes the series impedance for our voltage source. The reason I like to leave it in rectangular form is because this X component is always the resistance of the circuit, and this imaginary portion is always the reactive portion. And the plus and minus means whether it's a capacitor or an inductor. Okay, so if it's a plus, that's an inductor. If it's a minus, that's a capacitor. So when we draw this back, we can draw this back with a 2.65 ohm resistor and 4.41 ohms of inductive reactance because of the sign. Again, these two are equivalent, so if we placed a load between the terminals on either one, we should see the same current and the same voltage there for each. And that's just a quick